So welcome. As I said, my name is Jorge. I'm a data scientist from Chile, and I work in bitgrit in Tokyo, Japan. To start, I want to talk a bit about bitgrit. Bitgrit is a data science platform that has competitions, a job board for data scientists, and our end goal is to have a fully functional AI marketplace where companies and engineers can exchange algorithms and payment freely on a blockchain platform. In our case, the competition part is, in simple terms, just like Kaggle. So if you've heard about it, I like to say that bitgrit's goal is to connect data scientists with real problems and real companies. Okay, so in today's webinar, what we're going to learn is why and how to join a data science competition, how to design and train a simple machine learning model for this competition. We're going to show a few examples how we can improve our score using more data, changing things a bit. And we're going to create a final solution predictions and submit it to the platform. Yes, I will share a presentation after session. Please let me know if you don't hear or have any problem. Yeah, I'll try to answer more technical questions in the end. So yeah. Okay, so what are data science competitions? Data science competitions are fun and structured ways to solve real world problems. They're not only great for companies who can solve problems via crowdsourcing, but also they're great for participants for many reasons. First, I think it's one of the best ways to learn data science, or well, anything for that matter, which is doing it by yourself, experimenting, trying new things. Second, you can win big prizes if you submit a solution that's good enough, which is also kind of nice. Another reason is that you can actually experience, working with real world problems usually for organizations that, they have a problem that they can't easily resolve it themselves. They need a team or even more resources to solve it. So, they go to these crowdsourcing platforms. So these are real world problems usually, and they're pretty interesting. And also, some of the boring part of data science is already done. Most of the time, you still need to, understand the data, handle the data before attempting to put it into a machine learning model. Just like how it works in the real world. Finally, I think recruiters and companies really like and love applicants with experience in data science competitions, especially in competitions. So they are a very good addition to your resume or GitHub or your LinkedIn, especially if you get a good score, because it shows passion. And yeah, it's in general, I think companies are really interested in people that have experience in competitions. So now let's talk a bit about this competition that we're going to join today. This one's a fairly simple one. It's organized by Data Gateway, and its goal is to see if we can predict the number of views a video can get. As many of you know, online video platforms like YouTube allow creators to upload videos and get money in ad revenue if their videos are popular enough. Of course, now creators want to get as many views as possible in their videos, so that's why they try to optimize their video metadata so that they are more likely to become viral. So currently there are no strict rules that determine which videos go popular, but we'll know that it's kind of a mixture between using clickbait titles like this 5 exercise will change your life, or thumbnails like with people doing surprise faces, and it also has a lot to do with the recommendation algorithms underneath these platforms that decide like who to show videos and how many people to recommend certain videos. So yeah, so more specifically, what we want to do is predict the number of videos a video can get, I mean, the number of views a video can get in a certain amount of time. And how we do that? We use data and metadata that the user can control, like video title, the description, for example, if they use certain keywords, the thumbnail image, other metadata like duration, language, tags, etc. Okay, so if you haven't already, let's please join now the competition. So first, please go to this following URL here, and then click on participate on the upper right corner. If you don't have an account, please register now. So yeah, let's wait a couple minutes for people to register. So after you register, click again on participate. That button over there to the right, and accept the non-disclosure agreement, please. After you join, you have to refresh the website and go, and a new tab called resources will appear there. So there you can click there to download the data. It shouldn't take too long. So yeah, meanwhile, please also check, quick the overview, take a quick look at the rules. Let's try to continue. So now let's talk a bit about the data. Hope you had a chance to download it and unzip the files at least. So as we mentioned before, we have four main types of data, which is metadata, which includes what we want to predict, the number of views, as well as other things like duration of the video in seconds, the aspect ratio, the day of the week it was published. We also have the title of the video, which was vectorized to 50 dimensions. So what does this mean? It means that each title text was converted to a vector of 50 numbers. The same thing was done for the description data. And finally, we have our thumbnail data, which was processed by taking all pixels and then applying some methods to reduce the file size to 4,000 dimensions. Okay, so how does this vectorization of text works? As you may know, to train or predict using a machine learning model, data has to be in the form of numbers. So it can be text, can be files or emojis, any other thing. Has to be numbers. So to be able to use text data in our models, we need to convert it to numbers in some way. And how many of these numbers we're going to use to represent text needs to be a fixed number for all examples. So we need a fixed amount of numbers to represent any text that we want to use in our model. So we do this with something called text vectorization. And so what is text vectorization? I won't go into too much detail since I'm not an expert, but there are a couple of popular ways to do this. For example, you could have a big dictionary with all the words in the language of the data you're using. Count the number of appearances of each word in a sentence to get an array of numbers. The resulting array would be the size of the number of words in your vocabulary, with mostly zeros, since most words in a language do not appear in a short text. And that, of course, could be too big for practical reasons. It's usually too big. A common way to do this is to use something like word2vec, which is basically an algorithm that maps each word into a numerical space, for example, a 3-dimensional space, so that semantically similar words are close to each other, and semantically different words are far away from each other. So now the different coordinates in this space represent different forms in which these words can differ, be different. For example, the word man, as we can see in this picture here, would be a point in this 3-dimensional space that is close to other point representing the word woman, because they are, semantically similar words in many ways, but they would fundamentally be different in the gender dimension, right? So let's say there is a gender dimension that is automatically, decided by the algorithm. And that means that words like, king and queen would differ mostly along the same dimension, as well as being closed in other dimensions, right? Since they are also very similar in many other ways. So in this other example, we can see that another dimension will represent the verb tense or similar temporal characteristics of a word. So naturally, words like man or woman wouldn't be different along this dimension. I mean, this new dimension, because they don't have any tense. But since they are temporal, but words like walked and walking or swam and swimming, would differ similarly, like along this other dimension. So in the right side image, we can see that a man and woman would share very similar values for 3 out of the 4 coordinates, this fourth dimensional space. So only the last one appears to be different. So we can assume that the last one encodes the gender difference. If we take a look at the coordinates for king and man, we can see that they actually share this last coordinate, which may be, the male coordinate or something, and also the third one. So what can we assume from this? We could assume that, for example, the first 2 coordinates have something to do with semantics of these words, like if they have anything to do with royalty, for example. And we also think that the third coordinate encodes that these are humans, right? Because which applies to the 3 of them, right? So, and so on. Okay, so in general, much bigger dimensions are used. For example, our data is encoded into 50 dimensions. And yeah, also in our particular example, we're not working with individual words, but with sentences. And we actually didn't really use word2vec, but more, current and sophisticated algorithms that expand this idea of, mapping words into numerical spaces. So the study of text vectorization and other things is the main subject of what we call natural language processing, which is a whole new world in itself within machine learning. So if you want to learn more about this, well, we have some links, and just take a look at natural language processing, or NLP, which is it's a pretty hot topic. So the important thing is we have numerical representation of text that is quite consistent and allows us to have similar numerical vectors for similar texts. Okay, so okay, so to train our model using this computations data, we'll use an algorithm called XGBoost, which is a special implementation of gradient boosting algorithm. So some of you may have heard about it. It's quite a simple but very powerful algorithm that can be used in many different scenarios. It is widely used to run quick tests with the data, since there isn't much tuning required to achieve great performance, like compared to neural networks or other more complex algorithms. I always recommend starting our models with this kind of boosting algorithm or trees algorithms, they're very good. They're actually very powerful, and they win competitions usually. But and they're also easy to use, so it's a very good starting point. So again, I won't go into too much detail about this, but basically, gradient boosting is an ensemble of many decision trees. In a decision tree, it works kind of like this. So let's say you have 2 classes, 0 and 1, and our input data has 2 features, color and underline, like we see in this above image. So the features are, color, so it's red and blue, and underline and not underline. And so for each feature, we separate our data into the existing categories. So we start with the color. For example, this is red. So if one of the remaining classes, as in our blue class here, for example, can be divided with any other feature, then that branch of the decision tree ends there, because that if it's blue, it's gonna be 0, right? So that's your prediction. And And if it can be divided, we divide it again, and so on until we can't make more divisions. So we end up with some way of splitting the data that lets us decide if it is 0 or 1. So that's, it's in very roughly how a decision tree works. So in the end, a gradient boosting tree or gradient boosting decision tree, what it does is an algorithm that creates these trees one by one and calculates the error and goes improving each tree based on the feedback from the last one. So, you create 100 trees and each tree is going to be, better than the one before. XGBoost is just a, special implementation of this gradient boosting algorithms, which are very, very popular right now. And, I think it's the best for general purpose data. So if you don't have something very particular, for example, if you have image data, but actual image data, not processed image data, high resolution stuff, and then you can maybe achieve a higher accuracy using something like convolutional neural networks. But in general, this is a very, very good starting point. Okay, so finally, to give an example of how someone's input may look like. So, after examining our data files, we take the data from the different files that we want to use. We join them and create a concatenation of data to form a big vector X for each example. So our target value will be then the number of views for a particular video on the example, and we will call this Y. And finally, we train or feed our algorithm with thousands of these examples so that our model, can make predictions on the test data later. So this is like, how it can look like. We have a competition ID, we have duration, some metadata stuff. Then we have, the vectorized title, which is, a bunch of float numbers. Same with the description, and then same with thumbnail. So and then, the target variable should be Y, which is what I want to predict. Okay, so now please, if you will, open your Jupyter Lab or Jupyter Notebook. I hope you guys could, understand, download the data and open your notebooks or lab. I prefer lab because, you can see the data files to the side. That's a bit more, a few more functions. That's, I think it's better. Okay, so let's create a new notebook. Hope you downloaded the data and put it in a folder called, competition data or something. So we have our data here. Okay, so we create a new notebook. And okay, first thing we'll do is import the pandas library, which is a very important and powerful library for data science and data analysis in general. So, wait a second. Okay, so with pandas, we can do a lot of visualization and data processing. So it is important to understand how to use pandas. If you want to work with Python and anything that's data science, I really recommend using pandas. If you're not familiar with it, don't worry, since we're not going to do anything too complicated. We also share, a few resources where you can learn more about. But the internet is filled with tutorials and courses and anything. If you look for data science, you will come up with pandas. If you don't have pandas installed, you can install it right here directly using this command. So I have installed, so that's why it shows that. But then, okay, it's and another two important libraries that are frequently used together are NumPy, which is another very it's a very popular also library that helps with mathematical operations for matrices, vectors. It's like a very efficient mathematical library for Python. And also we have a very popular machine learning library called scikit-learn. This is very complete and has many algorithms pre-installed, many methods for data preprocessing stuff. So it's also a very good starting point. It has implementations of very new algorithms, so it's a very updated library. So it's really good. I really recommend it. Okay, so now we import our libraries using these commands. Let's start with just these two. Okay, so I like to use tiles and markdown in my notebooks, so everything is more clean and organized. So let's create a new section here that we call read data. Okay, so it's very important to understand and do some visualizations of your data before anything else. We see that we have a lot of different files here. So like metadata, title descriptions, thumbnails. And so as we discussed, text has already been vectorized, so we don't need to worry about doing that ourselves. So image data corresponds to that value of each pixel. Yeah, where is it? Oh, it's already here. Yeah, so it just corresponds to a reduced version of the pixels of each image. Okay, so let's start with our train data. So can make a smaller title here called train data. It's a bit smaller maybe. Okay. So first let's take a look at our files. So we have we'll call this meta train. So we can take a look at our files using our pandas read CSV for reading comma separated values. And then I'll just copy this one, and edit it. So the second one is the description data. And then we have image string data, and then we have, title data. So we change it here. Now it's train description, train image, train title. Okay, so we can run that, and we are reading our files. So a good idea is to, when we have different files and stuff, a good idea is to take a look at the shape of our data. So because we need to handle it in many ways and put it together, so it's important to be aware of what we're dealing with, and also to understand if we know how much data do we have, like in numbers. So we can just do this. So dimension of metadata is train.shape. That's where we use the shape. It's not a function. This is an attribute of our data. And let's just copy these two so we can, be faster. So this is description data, description train. This is image data, image train, and this is style train. Okay, so we run this and we see that we have, these are the dimensions. We see that we have 3,000 train examples. We'll see that the only file with many columns is the image data, which was vectorized. This is pretty natural because we are talking about pixels. So Okay, so then I recommend always to use the head method to take a look at it. But let's first start with the metadata, right? Which is easy to understand. So we can use the head method to take a quick look at the data. Okay, so we can find here things like ID, if the ads are blocked, if the video can be embedded, aspect ratio, duration in seconds, language, blah, 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 number of likes, number of tags, day of the week, hour of the week. Yeah, of course, the most important here is the views variable with views column, which will be our target value. So the value we want to train to and predict. So another very important thing to do with this kind of data is to check for null values, right? So we can do that very quickly using the is null method, and then we can sum for each column. So if we do that, we get something like this. So we have each column, and then we have the number of null values. So fortunately, this time we don't have any null values since the data weight was pre-processed. So we don't have to get rid of anything. But if we had to, we have we have to do something, like get rid of the rows or columns that contain too many null values. Okay, now let's take a look at some of these variables. For example, let's try to find, let's try to take a look at the hour variable, to see the distribution. So to see the distribution, we can use the histogram command. It's called hour, so hist, to create a histogram. So we can determine now how many beans, like how many pieces we want to separate the data. And since we have 24 hours, we want to use 24 beans. So if you do that, we get this plot. Okay, this looks like a fairly typical hour distribution plot, with low frequency parts, which tend to be nighttime. In this case, it appears to be a bit shifted since the most popular time is around 5 and 6 a.m. So yeah, well, these videos were taken from different places. So we can assume it has something to do with time zones. But we have to remember here that it really doesn't matter if it is shifted, as long as all our data has the same distribution. What important is consistency. So okay, now let's take a quick look at the day of the week. Oops, day of week. And again, these are 7 days of the week. So here. Okay, so this is very interesting. We can see for some reason we don't have video data on our data set that was uploaded on Friday. Yeah, because this starts on, I think this starts on Sunday. So it's Sunday, 1 is Sunday and 7 is Saturday. So 6 is Friday. So for some reason there's no data on Friday. That's a bit odd. But I guess that's just what our data says. So yeah, we also see that we have, most uploads are on Monday and Saturday, which kind of makes sense. But yeah, that's just how the data we have. Now let's try to take a look at our target variable. Let's go. The views. So we take meter train and we go to views. You could try to take a look the same way that we did above, using histogram. Let's say 20 bins. Okay. So this plot isn't very useful because the distribution of the data, this is a exponential distribution, and it contains a few outliers. that your histogram too much to the 10,000. So when we have this kind of plot, we can better visualize it by using a logarithmic plot. So to do this, we can just pass our column through a NumPy function called log10, which outputs the logarithm in base 10. So we just pass this directly, oops. Same number of ins. And if we run this, we can see, okay, well, this is a more understandable plot. Yeah, so this works way better for uneven distributions where you have a few couple numbers on the beginning, and then you have a big tail. So we can see that here that most frequent value is 2. It's around 2, so it's 10 to the 2, which is around 100 views. But we can also see that we get up to 10 to the 4, which is 10,000. So yeah, that's more or less the distribution we have. Yeah, we can now take a look at the duration. Let's take a look at the duration in seconds column. Oops, made a train, duration. Okay, same thing here. So we see that this plot is clearly skewed, and because we have a 20,000 around there. So if we repeat the same process, log 10, you can use log 10 or just log, which is natural logarithm. Anything, but let's just use 10 because it's easier to understand. Yeah. Oops, so we get an error. Okay, because we have a minus infinite. That means that we have something with duration 0. So, and which is minus infinite. So that cannot be plotted. So let's replace those values with zeros. So to do that, we can use a NumPy function called replace. So what replace does is we tell it which values in our array or matrix we want to replace and with what. So we want to replace this NumPy numpy's minus infinite values for 0, for the purposes of this plot. So we do that, and then let's try to see if we can plot this better. Oops, what did I do wrong here? Oh, this goes here. Okay. So we get yeah, this is a fairly normal distributed plot. Just much nicer, and tells us that most of the values are also around 10 to the 2, which is around 100. So this means that a great part of the videos are between 1 minute and 2 minutes. So it's good to know, So before moving to another file, as a general rule, remember that we have a plot like this. Anytime we have a plot like this, it's recommended to to apply some sort of logarithmic function, to transformation in order to transform the original exponential distribution, which has that shape, to a more normal distribution, right? Which is better it's easier to visualize, it's easier to understand, and sometimes it's even better to pass to the model the data transformed like this, because we don't have to big changes. Okay, so now let's go to another kind of data file. Let's go to, let's say, the image data. Okay, now let's take a quick look at the image data using the head command. Wait, how is this called? Oh, it's called image train. Okay, so yeah. So we can see that each one of these columns, each one of these values represent 1 pixel on the image, but the quality has been reduced. So we ended up with only 4,000 values. And there's also some negative values because you say that was normalized to be in the range of -1 to 1. So there's really nothing much we can do with this data for now. So, okay, let's leave it as it is. I have a question. Why do you have minus infinite values in the data set? What does that actually mean? Okay, so the question, so we don't have minus infinite values on the data set. We had here a minus infinite after applying the logarithmic function to the duration. So the duration contains some zeros because, I don't know, the data is flawed. It's not perfect. So apparently there are some videos that have 0 duration, right? Which is it's very odd, but who knows? So if you have a 0 and you pass a 0 to a logarithmic function, you get minus infinite. That's how the function is. So because we were trying to plot it using a logarithmic function, if we pass a 0 value, we will get this kind of minus infinite. So that's why we have to process them. But the data itself doesn't have minus infinite, and it really doesn't represent anything. It's just the transformation that we try to do. But since we just really want to, visualize it, we can just, get rid of those that way. Hope that answered your question. Wait, okay. So moving on, yeah. So yeah, this data, there's nothing much we can say about this. It's very, this just data, very pure raw data that we can, just input in our model. Here we have our IDs, video IDs. Yeah, so now let's try to take a look at some of the vectorized text data. So let's start with description data. So a bit more. Description data. So we do the same. We take a look at it using head. And yeah, same thing. We can see we have here 50 dimensions. It's up to 50. So each one represents one coordinate in this 50 dimension space. I know it's hard to visualize, but it means exactly what we discussed before. We may have some gender space, some past or temporal, dimension, gender dimension, whatever. The algorithm decides, and these are not very super specific, but this is just kind of what the algorithm decides that text vary between. So as we discussed, similarly, similar vectors here would represent similar text, and very different vectors should indicate very different texts. Again, we could try to plot this data, but I don't think there will be anything too interesting here because it's just, very, not random, but this is a, complex space. So let's just keep going for now. Finally, let's take a look at the title data. Oops, nope. Okay, so run that. Yeah, this is very similar to description data, and that was also vectorized using 50 dimensions. So again, similar vectors represent similar titles. Okay, so we have a question, I think. How to convert text to number in all columns in all files. Okay, so numerical files. Also, when as I discussed in the first presentation in the PowerPoint, you have to do this using an algorithm. There are many different ways to do this. One popular way is using word2vec algorithm, which maps this, takes a text and kind of says this text is similar to this other text, so let's put them together, and then takes another text and says, oh, this is not too similar, so let's put it more far away. You can picture a 3-dimensional space. It can be done to words, and there are some other algorithms that can work on sentences or like longer. So you don't have to convert the text yourself, because we already did that for you. But if you want to understand that, that's mostly how it works. You take the text and you process a lot of text at the same time, and then put those together, trying to figure out which words appear more commonly together, which sentences or which words never appear together. So if two words are never appear together, they're very different words, or for different contexts, and maybe very much far away. So yeah, that's basically how it works. But you don't have to worry this time, because we already converted the text to numbers. So it's just numbers for now. But if you want to take a look at it, take a look at word2vec, which is written, this is it's a simple algorithm. It works mostly on it's for words, but it's very useful to understand, how most of these algorithms work in the core. And also, you just take a look at Google for natural language processing. That's a very hot topic. It's a whole new world within machine learning. So yeah, I'm going to continue now. So again, also, as I said, you're welcome. As I said, different different dimension represents different ways in which words can vary here. So here we have, instead, we don't have a 3-dimension space, we have a 50-dimension space, which is not something, again, that we can picture really, because humans only can see in 3 dimensions. But if we had more dimensions, it's ways in which things can vary. So usually the more dimensions, the better you can represent the data. But also, if you have too many dimensions, then it's hard for the algorithms to extract data if you don't have that many examples, right? Because you need a lot of examples to understand well each dimension. So if you have too many dimensions and not enough data, it's hard. So we have to, there has to be a balance there. In our case, 50 it's pretty on the small side, so I think we can do just fine with that. Okay, so now let's take to the test files. Take a look at the test files to see what's different. So we will call this test. I mean, tests are public, so this is what these public files here mean, which are the data that it's only input data, and we want to make predictions of. So we process the data, use the model that we train using the trained data, and make predictions, because we don't have the labels for the public test, public data. We have only for our trained data. So, okay, let's call this section tests or public data. And again, we can, description tests or, meta tests. So we meta tests. I'm just going to copy and change a few things here, because the names of the files are analog. So instead of train, this should be test. And instead of train, we should add public here. So let's try to run that. Okay, so we read the rest of the files. And again, let's take a look at the dimensions. Again, I'm going to do a little trick here to just copy, paste, and dimension of, okay. So this is test, 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 and test. If you run this, we see that we now have 986 values that we have to predict. So we have, 986 data points as compared to the 3,000 that we have for training. So we have to predict the number of views on 986 videos. The dimensions are the same. We have 4,000 here for the thumbnails. It's mostly the same. Okay, so now let's take a look at metadata. Just for confirmation, and we see that we have which is the same columns here, except for the views. So we don't have a views columns as we expect because that's the label. The rest of the files should look, very similar to the other ones because they don't have labels and they're just input data. So again, we have 4,000 here. What a title test is mostly the same. Again, 50 dimensions. Okay. So that's input data for our model. So this is the part of the data that we use to make predictions. Okay, now we have taken a look at the data, and we've tried to kind of understand our data a bit. This part is very important, which is what we call exploratory data analysis, which is before you jump to create, a model or an algorithm, you need to understand the data, and for that it's very useful to visualize stuff, to make some plots, to take a look at, like manually take a look at the columns that you have, if there's, strange values, if there's strange distributions. It's very important to understand the data because if you don't understand the data, then you don't know what you're doing probably. So, okay. Okay, so now let's go to create our first model. We'll call this big section here, create model. So this one will be a very simple model as we only use the duration and language metadata. It's just a very simple model, just to test. So let's first assign our target variable, which is the most important thing here. And we can use the setIndex method so that we index our view count, we index it by the competition ID. So instead of having this 0, 1, 2, we have the actual competition ID that we intend. It's better just there later to join different files. So we take the views here. Okay. We call this Y as it's conventional for targets. Okay, so let's make a new header here. We call duration and language. Just what our input data is going to look like. Yes, let's take again a quick look at the metadata. Okay, and now always remember that your input data needs to be converted to numbers, right? But not just any number. We have to understand the nature of the data. So let's first start with the duration. Just an easy one. Okay, so duration, this is a very self-explanatory thing. It doesn't need much processing because this is just a time in seconds. So there's a clear numerical meaning, an order to these numbers. So we can just use it as it is. You could try, for example, to also pass these values through a logarithm function So you get a more evenly distributed, variable. But that's just, we won't do this for now. It's just, let's just use it as it is because it's still numbers. It still has a proper meaning. So now let's take a look at the language variable. Okay, now it might be very tempting now to just use this value directly in our model, because they're already numbers. But even if they're numbers, these are still categorical values, right? So categorical values represent different categories for each data point can be part of. So the thing is, most of the time, there is no particular order of this category, right? For example, if we had the categories apples, oranges, and bananas, what is the order there? So what would it mean if apples were 1, bananas 2, and orange 3? Let's say, yeah, those are the IDs that we give them. So apples 1, bananas 2, and orange 3. Would that mean that bananas are closer to apples than oranges are to apples? No, because they're just simply categories. They're just different things. So if we feed this value simply the number, like in one column, we'd be telling our model that there is indeed an order in that variable, right? So 3 is bigger than 2, and of course, and 2 is bigger than 1. So we're giving an order that it's not true, it's not there. So in the same way here, we have languages that could be, English, Japanese, Spanish, whatever, French, that don't have an intrinsic order. It's just different things. At least they don't have an order for this context. So one way to solve this problem is to convert this column into one column for each ID, and then put a 1 in the column that is the original ID, and a 0 for all the rest. So that is called one-hot encoding. To do that, we use a pandas function called getDummies. But first, in order to have our model more complete and robust to new types of data, it's good practice to add the categories beforehand. So if there aren't too many. So in this case, we have first, I think we have 10 categories. Well, I know that we have 10 categories. It's just a matter of taking a look at the data. If you want to confirm that we have 10 categories, you can do something like this. So this is not an order, but we can see that it's up to 10. So the value counts tells you how many of each value do we have in that particular series. It's a very, very useful command. But let's go back to head. Okay, so we first established the categories that we're going to split this column into. To tell pandas that these are all the categories, we can use pandas categorical dtype function. So okay, so first we create a new variable called language string. We use getDummies function for splitting this one column with different IDs into many columns with only ones and zeros. So we pass it our language column, and we tell it that it has a type. The language has a type, and the type has to be a categorical type, right? We could say it's date type or number type or string type, but this is a categorical type using the categories that we established. So we have to pass the categories to be the language categories. This may sound a bit complicated, but it's just something you'll get used to if you do it a few times. And okay, so we tell pandas, please split this column into different columns, dummy values like a 0 or 1, and split this value as a type of categories given by these categories that I am telling you. And we also add another parameter called prefix, which language we're going to use as a prefix. So since these IDs are numbers, this is just a 1, 0, up to 10. We add a prefix to know later what the ID represents, because we may have other IDs that are also numbers. So this is how it looks like now. No, it's language train. Okay. So if you see, you can see that each column now represents language, which can be anything like English, Spanish, Japanese, Korean, whatever. We can also see that only one of them is lit up for each row. So anyway, in case we have most here, 4 with the same, might be English, which is a common language. But only one of them is lit up. So yeah, one-hot encoding is a very common way to encode categorical variables. So as long as you don't have too many categorical, if you have 1,000 categories, then it's a bit tricky, because you will have 1,000 new columns, and that's a lot of dimensions that you add to your data. So it's harder for the model to understand what those each one of those columns mean if you don't give it too many examples, right? It's harder for the model to learn if you have too many dimensions. So if you have too many of these categories, it's better to use some other kinds of preprocessing, reduce the dimensions so you can better represent this. But for many times you don't have that many categories, so it's good to use something like this. It's called one-hot encoding, and you can use it just by calling this function get dummies. Okay, now that we have our very first simple data model, we can merge these resulting columns into one. To do that, we can call pandas function called concat for concatenate. And we pass an array of the series or the data frames that we want to put together, into one to create our X vector. So first we add an additional one, which is the ID, just to not lose track of which example is what. So we use the ID, and then we add the duration just like that, because we didn't do any processing. And we add the language, right? Okay. And we add them through the axis 1, and set the index to the ID of the computation. So we say axis equals 1 to indicate that we are concatenating columns, right? Instead of rows, but we could add, put together data like this, more examples, but we're concatenating columns, so we have more information for the same examples. That's what we're doing. And we can take a look at the result again with head. Okay, so we have the duration and all the language, columns. Okay, now we can, call this X for now. This is our current X. Yeah, now we have our input data. So first, to continue, doing our modeling, we need to import methods that we're going to use from scikit-learn. The first one that we're going to use is called scikit-learn model selection. It's called train test split, which basically allows us to randomly split our data into a trained set and a test set according to the percentage that we assign. The other one is the mean squared error from metrics, which allows us to calculate the mean squared error. And third, we're going to import a different library, which is called XGBoost, which is the library that implements our gradient boosting algorithm that we discussed before. So, okay, so we import these three values. And okay, then we split our data into a train test, a train set, test set. Okay, to do that, okay, give me a second here. I'll explain soon what this all means. 10, okay. So, okay, note that we already have public or test files. That's what I usually call them test files, but in reality, they are, let's call them public files, okay? So these are the ones that we need to predict, okay? This is the prediction files that, based on this data, we make new predictions, and those new predictions we uploaded to the competition platform, to bitgrit, we get a score. But when we are building our model, we also need to have our own, test file to evaluate if our model makes sense, right? We just kind of like train it and not know if how it performs before submitting it. So we still need to, from our train data, we still need to take a piece to for evaluation, So we can't really use this for evaluation because it does not contain target, labels. So to do that, we use this function right here, train test split, which outputs 4 values. What we will use as training, only as training. So input training data, input test data, label, training labels, and the actual test labels that we're going to see if how well this compare to the predictions that we made using on this data. So we pass here, we have to pass it our input data, our target data, the percentage of the data that we want to use as test, and a random state, which allows us to obtain the same values, if we run the experiment. It can be anything, but I found that 10 works well in this case. So if we run that, okay, we have to split the data. Okay, so now just for clarity, we can print again the shapes. I recommend that. Training set shape, train shape, and test set shape. So as you can see, our data got split into this is 30%, which is 900. 2,100 is the actual training data. So if you sum this, you see that we have the original 3,000 training, training examples. Okay, so yeah, looks fine. Now, machine learning algorithms don't need just data, they need hyperparameters, which we can adjust to try to reduce the error and avoid traps like overfitting. So of the training data. So XGBoost allows us to pass hyperparameters as a Python dictionary. So we call this params, for example. And we'll only use 2 here, but there are many more parameters that you can change of the algorithm so that it trains a bit different. And dynamically adjusting these parameters based on the feedback from the experiments that you had to do is called hyperparameter tuning. and it can be an important factor to increase your model. So the first parameter that we're just going to pass is the number of boosting rounds that we're going to do. So each how many iterations of this series that we're going to create. This is just called number of estimators, and we will use 100, and then comma. Second one, it's called eta, which is the learning rate. So which represents how big of a step we take when we adjust our model for the next batch of examples based on the feedback. So we create a tree, we get an error, and then based on that error, we take a step. Okay, we say let's change things in this direction, this much. So the how much we change it, we can change it a little bit, and the training is going to be quite slow. But if you change it too much, you can maybe jump and skip some places of parameters that are at will, just for your model. So it has to be a decent value. I found that 0.2 it works okay for this one. So we establish the parameters as a Python dictionary, and we gonna create our model based on these parameters. So we will be using from XGBoost library something called the XGB regressor class to create the XGB busting model. Because this is a regression problem. A regression problem is a machine learning problem where you try to predict a number, right? You don't, instead of a class. So we import the regressor because we also have a classifier, which is for classification problems. And we pass the parameters like this. This is for passing dictionaries to Python functions. If we do that, we create our model, empty model with no data yet, but with parameters. And we can now simply train our model using the training data and the targets that we created above. So, second here. So we do this using the fit method, saying train, using the train input and the training labels. And we run this, and it takes very, like it's almost immediate because we don't have a lot of data. 2,000 rows of, what is this, 10 columns is a very small amount of data for what this algorithm are prepared. So it takes really a very short time. Then we can test our model using the RMSE on the test subset that we created. But first, we need to create predictions using the test data. This is a bit of a manual process, but we call this, Y predictions. It's model predict X test. So these are predictions of the test data. And then we calculate the root mean squared error. So the mean squared error is it's a very common error that we use to calculate how different are we from the actual numbers. The root mean squared is just taking the root of that, which is a number. It's a number that's closer to the original values, right? Because it's a square and then it's a root. So to do that, we just first call the square root using NumPy, and of the mean squared error that we imported before, and the mean squared error between the test and our prediction. So let's see what we get here. Okay, that's something, I guess. It looks big, but it's maybe not that big. It's something. It's a reference point now. Okay, let's see what changed if we add some more data, like the title data, for example. Oh, I'm being told that we have 10 more minutes. I'm gonna speed this up a bit. Okay, so yeah, so let's try to add the title data. Right, this has to be Markdown. Add title data. Since there isn't too much processing for the vectorized text, we will just add it to our X vector easily. Again, using the concat. Meta untitled train. We set the index to the competition ID so that it gets well put together. And again, we concatenate on the columns axis. So we do this, and then again I'm going to just copy this one. We split the data again using this function, and we take a look at the shapes again. So I'm just going to copy. You could do this in a more sophisticated way, but this is just easier. We see that we have 61 columns now instead of 11. So keep in mind that we only have 3,000 examples in total. So having too many columns might make the model hard to train since there are too many dimensions for the data. So we have to be smart when adding more data. It's not just simply putting all the data together might not work well in this case because we don't have too many examples. So finally, we create a new model and train it as we did before. Okay, so it's the same XGB regressor, params, XGB regressor, and then we call fit. Okay, took almost the same time. And then again, we can make predictions to calculate this, the test, and take again, the root means squared error to see if we have any improvements. Okay, we have some improvement. So using more data apparently helped us. Now let's try to create predictions using this new model and upload them to the competition platform. So to do that, we first need to transform. Oops, stay on page. Oh, my bad. Okay, I think we didn't run this. Oops. Okay, I'll just run everything again. Run all cells. It's gonna take a bit. How much time do we have, team? Thing is, yeah, like 4 minutes. Okay. Okay, we'll just make this quick. Okay, we have this error, then it stops. Oh, I didn't do the test. Oops, I'm getting an error here. I don't know why. This is not good. Train. Oh, why train? Okay. Yeah, I was passing it there. Okay. Also, okay, so we fit the model and now we can oh wait, I am stuck here and we took the square root means squared error of the between y predictions and y test. and this, wait. It's not right. Should be different here. Oh, I haven't made the predictions. Okay, sorry. So we do predictions. Well, model can predict on the test. And okay, so yeah, that's the model that we have. Okay, so now we need to transform our test data. To do that, 2 minutes. Okay, we have 2 minutes. I'm sorry. So we create a duration test, which is the same. We have to apply the same transformation. But to the test data, I mean the public data. Okay, and then we have the language data. We need to apply again the same transformation. We just copy this one and put it here. And instead of train, this is test. Same categories. And just as before, we create a final X thing. Instead of train, it's going to be tested. Here 2, here 2, and then here 2. Okay, and finally, we do the same thing. So X test is concatenation of this 3, but instead of train, this is test, and instead of title data for the train, this is test. And finally, we make predictions on the test data. Again, but we don't have anything to compare. So now we need to compare this to the appropriate formats. So to do that, we create predictions, index is the index that we have. And then we save these predictions to CSV. Put it, I don't know, submission1.csv. And we add index false, so it doesn't add another index. Okay, well, you can try to upload this file to bitgrit. We need to end this now. We're very short on time. So yeah, with this, we created a new submission file using our model, and we can try to upload this to the platform. You can try to improve your model on your own using more data or adjusting hyperparameters later, and you may find something interesting. Well, I can't upload the solution because I work at bitgrit, so that would be a bit wrong. But you can try to upload it using the submit button. And now I know that this competition doesn't seem too difficult, but it's quite complicated because we don't have a lot of data. So this increases a bit the luck factor on the competition, since randomness can play a bigger role than when we have a lot of data. So regardless, I suggest that you guys try different combinations of data, different algorithms, see if more data actually helps or even makes it worse, because that can happen. And in general, try new things, and see if you can get to the top of this challenge. Yeah, so I'm sorry that I had to kind of rush the last part, but it's basically doing same processing that you did on the trained data. I mean, yeah, on the trained data, and then do it on the public data so that you can make predictions using the model, and the model works on the same data, and everything works. So yeah, once you have the predictions, you upload it to the platform, and there you go. Thanks a lot, guys, for joining today. I hope any questions that you have, please let us know later. We'll try to respond to everything as better as we can. We'll try to, for the people that want to have access to this notebook, I will share it with you later. Yeah, please, good luck in the competition. Try new things, try more data, try less data, try new hyperparameters, try new algorithms. And as I said, it's a tricky competition. We don't have too much data, so we have to use it wisely. That's like my advice. Okay. So I think I'm going to quit sharing now. Stop sharing. Second. Okay, thanks for joining today. I hope you learned something new today, or got motivated to join the webinar. We'll see you around on this bitgrit platform, bitgrit community. Please just take a look at the challenge. You may still have a chance to make it to the top. So thanks for joining today, and we'll sure will be the session recording upload somewhere. Yeah, I'm hoping so. So we have my team here. They're working on this. So yeah, the recording will be uploaded, so you can take a look at better. We will share it. Okay. Thank you for joining, and see you around, guys.